Hi guys, welcome back from spring break. I am going to get started today on chapter 10, which is all about conics, which is one of my favorite sections actually in this semester. And then we'll go back to chapter 9 after we finish conics and get into polar, and that's kind of where we're going to end for this semester. I really miss you guys. I really wish I could be giving this in person to you guys, but hopefully the lecture slides will help a little bit as we go through the last couple of chapters of the semester. Okay, so this is an intro to conics, and then we'll get kind of deeper and deeper into it as we go through. And that is my dog barking at the mailman right now. Okay, so we get a conic section by doing this. We take two right circular cones and we invert them one on top of the other. So those cones are the red things, and inverting them one on top of the other causes that hourglass looking shape. And then we take a plane, which is that blue rectangular sheet, and essentially we cut the cones with the plane in different ways to get different conic sections. So going left to right, we get a parabola by orienting the plane just so that it only intersects one of the cones. And then you guys can see that highlighted area is what gives us that parabola shape there, right? The highlighted area being that yellow line right there. Okay, a circle then is formed when we reorient the plane and intersect again just one cone. And essentially the plane is parallel to the ground, right, or the surface that the cone is sitting on, and that's how we get that perfect circle. An ellipse then is very similar to a circle, but the plane is going to be angled a little bit so that we get an oblong circle, one that's longer on one side than the other. And then the last one that we're going to talk about in this chapter is a hyperbola. And that happens, it looks kind of like two parabolas facing away from each other. They're graphed slightly differently. That happens when we intersect both of the cones. We get that hyperbola shape. If you guys look around your house and you have a lamp with a lampshade, if you look at the reflection of the light onto a wall that the lampshade creates, that is a hyperbola. That's the shape of a hyperbola there. Okay, I used to do this cool thing with a flashlight. Obviously can't do that now, but hopefully we've got that kind of visualization of conic sections. All right, there are really, really important equations that go with each type of conic section. If we were in class, this is something I'd have you guys memorize, but just if you're taking notes, maybe jot this down. For a circle, really, really important pieces of information. We can tell whether we have an equation of a circle if both the terms are squared, the coefficients of x and y are the same, could be any number as long as they're the same, and they have the same sign. Right? That gives us a circle. This is the standard form of a circle. X squared over a squared plus y squared over a squared is equal to 1. We are going to note every single time we write the equation of a conic section, we will always make it equal to 1. That is something we call magnification form. And that is something you will hear me talk about for the rest of this chapter. Okay? Always wanted a magnification form. That is the form that is going to give us the most information about any conic section so that we can graph it. An ellipse is slightly different. Both terms are squared just like a circle, but the coefficients of x and y are going to be different. That means that the number in front of x and the number in front of y should differ, but the signs will be the same. Okay? Again, to get magnification form, we make sure that we have everything equal to 1. Like I said, that will help us get the center and then the radius of the circle, or the various distances from the center for an ellipse. Okay, hyperbola down here, bottom left. We know we've got an equation for a hyperbola if both the terms are squared, but the signs will be different for x and y. So one term will be positive and one term will be negative, and that is always true for a hyperbola. Again, magnification form because we have our equations equal to 1. The last type of conic section is a parabola. We actually did a whole chapter on them last semester, if you guys remember. There are two equations for a parabola. Only one term is squared, so we know we're looking at an equation for a parabola if we only have x or y being squared, but not both. we have two different types of parabolas. So parabolas that open up or down versus parabolas that open left or right. Now we have an up or downward facing parabola when x is being squared. The way that I like to remember that, I'll show you guys a little bit later, but also in Algebra 1, you guys graph x squared, which is the upward facing parabola, and then the parabola that has the y term being squared is the parabola that's going to open left or right. Remember, HK is the vertex on both cases, so we'll always want to graph the vertex. All right, so shifted equations, though, look a little bit different. So what happens is we take the standard equation, and what happens if we're looking at a circle whose center is not 0, 0. The last slide showed equations where the center of the circle and the ellipse and the hyperbola were at 0, 0. We're just going to add these h and k values in order to represent the circle, ellipse, or hyperbola being shifted. Okay, so these are really the standard equations. We can always substitute in 0 for h and k to get back the equations that we had on the last page. But these are just equations that are really important in memorizing in order to help us better graph these later. Okay, so first set of examples, just like really quickly in your own mind, if you can go through this and kind of identify what type of conic section we've got, it's going to make your life a lot easier when we go into the harder things later on in this chapter. All right, so for example, 3x plus 2y squared is equal to 7. Only one of the terms is squared. That means that this is a parabola. We don't really even need to know anything else. Just one term being squared is always a parabola. If we go on to number 2, this is the case where we have both x and y being squared. One is positive, one is negative. This is that case where we have a hyperbola. Number 3, x and y both being squared. Their coefficients are both 5, so they're the same. This is a circle. This, number 4, kind of a trick question. No terms are being squared, so it's none of our conic sections. This is just the equation of a line if you think back to Algebra 1. Number 5, you've got x and y being squared. They're both positive, but the coefficients are different. That yields an ellipse. Okay, so I'm going to challenge you guys to pause the video and think about identifying the rest of these before I give the answers. Okay, so take a minute, pause. I'm going to keep going though. Here we've got x and y, but this is kind of a trick. We've got x and y. We would want, though, all of them on the same side in order to determine their signs. So if I were to subtract 10y squared from both sides, that would get x and y on the same side, and then we'd see that one is positive and one is negative. So this is the case where we have a hyperbola. Number 7 is a little weird. This is another trick question. So x squared plus y squared, that's a circle. The coefficients are the same in front of x and y, and they're both positive, but we can never have a circle that has a negative radius. I would say we've got a radius of -5, and that can't be true. So that's nothing. That's undefined. Number 8, if I go through these a little bit quicker, this is an ellipse. Number 9 is also an ellipse. Number 10 is a hyperbola. All right, and then one more just to kind of review some of these other trickier ones. Again, I'd pause this, see if you can identify them, and then replay once you've got the answers. Number 11 is a hyperbola. Number 12 is a parabola. 13 is a line, one of those trick questions. Number 14, undefined. 15 is a hyperbola. Okay, 14 is undefined because if I subtracted 64 from both sides, you'd end up again with a circle that has a negative radius. All right, so now that we know how to identify conic sections looking at the equations, there's one more thing we're going to talk about, and then we're going to do a couple of examples. So there are these things out there called degenerate conic sections. Super weird way to kind of identify something mathematically, but here's what a degenerate conic section means. Go back to those cones that we have and that plane, and that's how we get those conic sections. There are specific cases where the plane intersects the cones in a really weird way that gives us something we call a degenerate conic section. So, case 1, when the plane goes through the points where those two cones intersect, we get a single point. That's going to come from looking at the equation of an ellipse and only being able to graph the center, or a circle. Okay, second case is a line. We're not going to really see this case mathematically in our homework. That's when the plane intersects parallel to the sides of the cones. Kind of hard to see with just a picture. And then the last case is if we took that plane and stuck it directly down the middle of both of those cones, we get those two lines that make an X. That is what happens when we see a degenerate conic section coming from the equation of a hyperbola, and all we can graph are the asymptotes there. The equations, how do we know we've got something that is a degenerate? When we go to write the equations in magnification form, we're going to do an example of that in just a moment, we will see that the equations end up equaling 0 instead of 1. And then we know immediately that we will have a degenerate conic section. And we will not see those cases for a parabola. That's the case where we get the line. And that comes from something we'll talk about later called the directrix.